So something else I wanted to just talk about this slide for a second, because I kind of ended up with the volcano description a little bit late there, is that you'll notice that the different types of plate boundaries also have different types of volcanoes. And we'll talk more about that later. But if you look right across around here, these are the convergent plate boundaries, and they all have stratovolcanoes. And remember, stratovolcanoes are the ones that have the intermediate magmas, or the magmas that are more felsic. And the reason they're more felsic is because you have this oceanic plate going down, cooling off, and melting down below, coming back up through felsic material to form these more dangerous, thicker viscosity magmas to form a island arc. Okay? Not an island arc, sorry, a volcanic arc. So lots of stratovolcanoes. Okay? Now, the same thing can happen in an oceanic crust. We have two oceanic crusts, one going down, melts, and then that material comes back up. Now remember, when you have a melt, as it cools off slowly, it will become more and more felsic. So as it goes up, it's going to become a little bit more felsic, forming still stratovolcanoes, but they're not as dangerous as some of these ones along the coasts. Here. These island arcs are still dangerous, but stratovolcanoes, but not as dangerous as before. Now, along the divergent boundaries, all these volcanoes tend to be what we call either cinder cones or shield volcanoes. They're all up and down where we have divergent boundaries. Now here's a good example of a divergent boundary, but this one is a divergent boundary that's coming up through continental crust. So this is like the Great Rift of Africa. And therefore you have a mixture of both shield volcanoes and a mixture of stratovolcanoes. Like Mount Kilimanjaro is a stratovolcano. But a lot of the other small volcanoes throughout here are shield volcanoes. Okay, because it's a mixture of both the mafic stuff that's coming from the subsurface, from the asthenosphere, and the felsic stuff as it goes through the continental crust to form the stratocones. Okay. Now remember, shield volcanoes are from mafic material. Well, why are they mafic material? Because that material is coming from the asthenosphere. And if you remember, the asthenosphere is also mafic, or even what you might think of ultramafic. And as it goes up, it forms shield volcanoes that are mafic. So once again, it went from ultramafic to mafic, therefore becoming more felsic as it came from ultramafic to mafic. Get it? Okay. Anyways, we'll come back to that later as we make the connections of volcanoes to plate tectonics. But it's an important thing to start understanding. And there will be, I'll promise you, there will be questions on how making these connections from the igneous sections to plate tectonics over time, and the volcanoes and earthquakes when we talk about those later. So, which is hard for students. It's hard for them to make the connections between all the different units and put them all into one idea. And that's what plate tectonics really does. It brings all these different ideas together into one. But you have to use the data from each of the units to be able to understand that. Okay. Now another way that we are actually understanding or be able to figure out how these earthquakes work. Let me move this a little bit. There we go. Okay. How these plates move is that we're using modern technology. We're using what we call GPS units. We're putting GPS units all over the world, and we're basically cementing them into the ground. And we're actually watching and having the GPS units run all the time. And what we're noticing is that the GPS units are actually recording, the movement of the continents. They're very small movements every single year. A lot of times it's only the movement of maybe your fingernail. Okay? But they're moving. So there are some places, for example, out here in the Nazca Plate, where we have these really fast movement, if you remember, are moving on rates of about 17.2 centimeters per year. Okay? In some places, even up to 18 centimeters per year. Whereas other places, like here in the Atlantic, they're only moving about 3 centimeters per year, so much slower. Others, even slower, 1.7 centimeters. Okay? So they range anywhere from 1 centimeter to 18 centimeters. Now, why the difference? Well, it's often because in the subsurface, we have some places that are hotter than others. And if they're hotter than others, they're going to move faster, or the density of the material is going to move faster, and therefore you have faster moving plates. Okay? Whereas places that it's a little bit cooler, they're still rising in the subsurface, but not pushing things apart as fast, and therefore those boundaries aren't moving as fast as others. Okay? So for example, around the Pacific, it's moving really quick because you have those fast moving plates. Around these regions, not as fast. So you have more earthquakes and volcanic activity around the Pacific than you do in most other places around the world. Okay? Okay. So what defines the location of plate boundaries? It's a lot of things. Okay, it's the location of abundant earthquake epicenters, the high mountain belts, the coastlines of continents. These are all true, right? This was supposed to be a trick question I did for my students in class, and it's the high mountain belts work, the location of abundant earthquake centers work. The coastlines of continents don't necessarily work because it really depends on if there's a continental crust below there or not. And so the real answers here is either A or B. Okay, so remember topography, volcanoes, location of earthquakes, all of these did help us to delineate where the earthquake boundary is, or our plate boundary is. Now the closest plate boundary to us, if we went east, the closest plate boundary to us would be actually in the East Atlantic rise. Sorry, the Mid-Atlantic ridge, okay, which is in the middle of the Atlantic Ocean. Now if I went south, the closest one would be actually near Haiti. Okay, and we'll talk about that a little later, but it depends on which way you're going. But the closest one to us to the east is absolutely in the middle of the Atlantic Ocean. So our North American plate is actually made up of both continental crust and oceanic crust. That's something that students have a hard time remembering. Okay, so just a couple things to remind you. The lithosphere is that outer rigid crust and the upper mantle, just the portion of the outside of the mantle that acts rigidly. Okay. And the crust at the very top portion of that. Okay, so you have the crust and then the upper mantle. That's all part of the lithosphere, and that's what's acting together. Now the asthenosphere, remember, is that material that's just below. Okay, that is actually quite ductile. Okay, kind of like what I showed you earlier, I think, with my silly putty. Okay, where something can actually move slowly over time. It's kind of this plastic. So this would be kind of like the plastic of my mantle, right? Okay, notice it's slowly moving. And so the hard crust would be over top of this, slowly moving over this weak outer, that lithosphere, which is the outer crust, would move over the weak inner sphere. That's why we call it the asthenosphere. Astheno means weak or plastic. Okay? And so this is the difference here. Now, if we put a load on top of my crust, it will push down and therefore bend that. So if I have a mountain on top of it, it actually bends down. It actually rides lower in the crust. If I don't have anything, it's going to ride higher on the crust, right? So just realize that. We'll talk more about that later when we talk about mountain building. But that's something that you should kind of remember. And put a load on something, it's going to sink. Just like putting a load on a boat, it will sink down, right? You take the load off, it will go up. Same thing happens to crust. Put something heavy on top of it, it's going to go down. Or if you put a lot of sediment on top of it, it's going to go down. If you have to take a lot of sediment off, it's going to go up. Okay? We'll talk more about that later. Okay. So before we talked about Harold Hess's idea of this seafloor spreading. Well, what actually causes that seafloor spreading? Well, what he suggested was what we call convection. It's that internal heat. Now remember, where's the internal heat from our planet comes from? That's an important question that we asked last time, and it's one that you're going to be asked again on the next test, I promise you. Okay, so where does the heat come from? Remember, it's not from fusion or fission or anything like that. It's not from the friction underneath the planet. It's from the radioactive decay of heavy elements. And as it decays, that heat will be released from the isotopes, and therefore cause places in the subsurface to be hotter than others. Now, if you have a place that's hotter than others, that material is now going to rise because it's less dense. And as it rises, just like in your bowl of mac and cheese or whatever you do, and you're going to cook that water, it's going to cook the outer surface, heating that water, forcing it to move up. And once it gets up, the temperature is now decreased, therefore it will move down, and therefore we call this convection. It's a lot like a convection oven, if you've ever heard of a convection oven. Okay? It distributes the heat throughout the system. Well, convection will move up, push that material apart, and push it down. Just like this one right here, where here's the hot source, moves up, pushes it aside, pushes it aside. Therefore, this is what we call ridge push, where it's pushing on the ridge, and therefore pushing it aside on each side, causing it to rise and push over. So this is convection. Now, convection can happen in a lot of different ways. It could be one big convection down from the heat source of the outer core, okay, all the way through the lithosphere, or it could be the smaller convection cells here, or stacked. We don't really know. It's really hard for us to understand what's going on under the subsurface. There are ways to do it, but it's hard to figure it out. We'll talk about that a little bit later. And I think we talked about it a little bit before, looking at what we call, in a sense, kind of like ultrasounds, but they're looking at seeing seismic waves in the subsurface to be able to understand the subsurface. But anyways, the point comes, it's convection. Now, once that ridge push, that buoyant magnet pushes up, driving the plates apart, remember this is hot, as it goes away, it cools off. Now you have this really cold material that's being pushed towards felsic material, therefore pushes down. And now once you have this really dense material, okay, it's denser than the mantle around it, it wants to pull down. If this pulls down, then it actually pulls everything else with it. And we call this slab pull. So in places where you have a trench, where you have an oceanic crust coming in contact with a continental crust, it's going to pull the crust down and form a trench in the middle. You see that little trench down in the center there? Okay, and as it goes down, this stuff down here is going to be really dense, and so it's going to pull everything down with it, and causing this to move faster. This is why the Pacific, the Ring of Fire is moving so fast, because on every side there's this trench that goes down, pulling everything with it. Whereas in the Atlantic Ocean, there is no trench on either side, and therefore it's only being forced by the ridge push. So moving slow here in the Atlantic, fast in the Pacific, because it has these subducting slabs. So in the Pacific you have mid-ocean ridges and converging, sorry, the divergent boundary and the convergent boundaries. But in the Atlantic, you only have convergent boundaries in certain places, and in the Atlantic, and in our neck of the woods in North Carolina, we don't have a subducting slab on one side. Okay, so it's not going down yet, and because of that, it's pushing both the continental crust and the oceanic crust in one direction. Therefore, we only have ridge push, therefore going slower. Okay, the stronger slab pull is a lot stronger than ridge push, and therefore it has a lot faster speeds associated with it. Okay, so this goes to this idea of what we call the Wilson cycle. The Wilson cycle is this idea of how the continents have changed over time. Now, if I started off with a stable craton, a stable continental crust, and then a plume came up underneath it and pulled it apart, you might have a sort of rifting. So we would call this a continental divergent boundary. Why do we call it a continental divergent? Because the divergent boundary is cutting apart continental crust. Okay, a great example of that in the world today is Africa, the East African Ridge. Okay, I'll show you some examples of these later on. By the way, you should remember these examples. They will come up in the test. I promise you that. Okay, I give you lots of different examples to help you understand the concepts and to tie them together in places that you might know about in the world. And the East African Ridge is a great place where this is happening. Right north of the East African Ridge is what we call the Red Sea, forming this small little oceanic crust in the middle of the Red Sea, pushing it apart to form this early ocean right here. Okay, so the Wilson cycle is really, to simplify this, it's really the way that ocean basins close and open. Okay, so you start off with that there, and you keep pushing it apart, you might get this full ocean basin. A great example of that today is the Atlantic Ocean. We have the Atlantic Ocean here with the oceanic crust, but no convergent boundaries on either side. So this would be Africa over here, North America here, and then here's the Mid-Atlantic Ridge pushing it apart. Now, if that kept going, at some point, this side over here might become so weak that it would break off from the continental crust and start diving down. And as it does, you now form a convergent boundary that can form volcanoes and things like this. A great example of where this is happening today, where one side is still attached and the other side is a convergent boundary, is where Africa is starting to move into Europe. So on one side you might have Italy and Vesuvius and all those other sides, and the other side is Africa. So that's an example of where it is today. Okay. Then if you keep closing it, okay, you might have the basin closing up. And this is also an example of Africa, because Africa is almost to the point of closing up the Mediterranean Sea. If it kept closing up, it would actually get to this, where the continental crust slams into the other continental crust. The oceanic crust is going down, but because the continental crust is dense on both, is less dense, they're going to ride up on top of each other, form this big mountain belt called India. this is an example of it today where India is slamming into Asia. So this is the cycle of what we call a Wilson cycle. We'll talk about this more next time.